Yeah, go ahead whenever you're ready.
Thanks, Ethan, and thanks to the organizers for inviting me as well. So today I'm not going to talk about fractons. What I'm going to talk about is what I'll call a hidden duality in a 4+1d topological order. So this is work that has evolved out of discussions involving many different people. So they're all listed here. Personally, I've been working very closely with Xie and Arpit on this project. So by topological order, what I mean is a gapped system that has a long-range entangled ground state, fractional excitations above the ground state, and a non-trivial ground state degeneracy on non-trivial spatial manifolds. So this is what I mean by topological order. And what's interesting about 4+1 dimensions is that there exist topological orders.
Yeah. Hey, Wilbur, I think this might be happening for many people. I can just still see your title screen. Is that intentional? Or over a whole system?
Title screen?
Is this happening to other people? Are you in like presentation
Wilbur's
mode?
face moving, but the slides are still on the title slide. So I don't know if you've changed the slides away from the title slide or not.
Yeah, I have changed the slide.
I'm only seeing the whole PowerPoint, not just the slide.
You can advance them by not being in the display mode.
I think the share screen is frozen. Maybe try unshare and then reshare.
Okay.
Quit.
Okay.
It just jumped back. Yeah, I think it's kind of like. Yeah, I guess we can see your mouse moving now. So
Okay. Wait, so are you seeing the second slide now?
Still, yes. Just I mean, you're not in presentation mode, but we can see the second slide.
Probably showing the presentation mode on a different monitor or something.
Oh, here, let me just unplug my monitor then.
Could it also?
Right. So yeah. So as I was saying, what's interesting about 4 spatial dimensions is that there exist topological orders that have loop-like excitations, but no fractional point-like excitations. So this is what we call a loop-only topological order. And 4 dimensions is the lowest dimension in which this occurs. So compared to 2D and 3D topological orders, relatively little is understood about these 4D loop-only topological orders. And essentially our goal is to basically gain a better understanding of this kind of system. So the simplest example of a loop-only topological order is the 4D loop-only toric code, which was introduced by these authors 20 years ago. And this model is essentially the topological order that I'll be discussing in this talk today. So this is an exactly solvable spin-half model with spins on the faces of a 4D hypercubic lattice. The Hamiltonian is essentially a sum of terms associated with the edges and the 3-dimensional cubes of the 4D lattice, and essentially has this form here. Right. So this 4D loop-only toric code is in some sense a direct generalization of the well-known ordinary 2D toric code. So it'll be helpful going forward to just quickly review the basic properties of the 2D toric code and then jump into discussing this 4D toric code. So as we're all likely all very familiar with, the 2D Kitaev toric code hosts Z2 topological order, and it can be sort of regarded as a Z2 lattice gauge theory. So the elementary excitations of this model are anyons. There are 2 sort of elementary types, the E and M anyons, which can respectively be regarded as gauge charge and gauge flux excitations. These are both bosons. And there's also a dionic excitation, which we call psi, which is the composite of E and M. So the anyons obey these fusion rules here. And basically, because E and M have this -1 mutual braiding statistic, the dion psi is a fermion. And the logical operators of this model have a very nice interpretation in terms of the sort of first homology and first cohomology groups of the spatial manifold. And so this is all very well known. So the 4D loop-only toric code, in comparison, can be regarded as a Z2 two-form gauge theory. So essentially, what two-form gauge field implies is essentially that the gauge charge excitations are loop-like excitations. And so this theory has a loop excitation, it's gauge charge that we'll call E, and in 4D, the gauge flux excitations are also loop-like, so we'll call these M. And there's also a dionic loop-like excitation, which is a composite of an E and M excitation, and likewise this is called psi. And so basically, sort of the fusion structure of this theory is essentially fully analogous to the 2+1d toric code, just that all of these excitations are now loops instead of point-like particles. And of course, these loops are created at the boundary of membrane operators acting on the ground state. So in this loop-only topological order, there's an analog of mutual braiding statistics. And so for instance, the E and M loops have a braiding statistic that sort of occurs whenever the world sheets of, whenever an E and an M world sheet are linked in 5D spacetime. And so in analogy with the 2D toric code, the logical operators of this 4D loop-only toric code correspond to second homology and cohomology. So in all these aspects, this model is really a sort of direct generalization of the 2D toric code. Okay, so one feature that is present in both the 2D and 4D loop-only toric codes is this so-called electromagnetic duality, which essentially permutes the E and M excitations and leaves the psi excitation invariant. The existence of this duality is sort of straightforward. It's sort of present just by looking at the form of the Hamiltonian, and essentially it's kind of a manifestation of the Poincare duality between homology and cohomology, and so this is very well understood. But the result which I would like to share today is essentially that the 4+1d loop-only toric code has an additional so-called hidden duality, which permutes the M and psi loop excitations and leaves the E loop invariant. So clearly, an analogous duality cannot exist in the 2+1d toric code because the M anion is a boson, whereas the psi anion is a fermion, and so this precludes any sort of duality that interchanges these two excitations. So just to be totally clear, when I say that this model has this particular hidden duality, to be totally precise, what I mean is that there exists a local unitary operator U that preserves the ground space of the model and maps closed membrane operators according to these transformation rules. So this operator U maps M to psi, psi to M, and leaves E invariant as far as it acts on closed membrane operators on the 4D hypercubic lattice. So basically, the existence of this duality came as somewhat of a surprise to us, because you sort of might intuitively expect that psi is on sort of different footing from E and M, and so that you would perhaps expect that this duality does not exist. But in fact, we have concretely demonstrated that such a unitary operator does exist. Okay, so this is essentially the statement of the result. Now I just want to sort of explain the intuition behind this duality and sort of how we were able to obtain this result. The essential idea is that this duality basically corresponds precisely to a particular kind of invertible defect that can arise in the 4D loop-only toric code. And it turns out that the easiest way to understand this defect is in terms of the sort of gauge theory interpretation of the model. So as I mentioned previously, this loop-only toric code can be understood as a Z2 two-form gauge theory, which essentially means that we can obtain it by starting with a 4D paramagnet with a Z2 one-form symmetry, and then gauging this this Z2 one-form symmetry yields the 4D toric code model. So the basic idea is that if we take this 4D paramagnet and imagine that it hosts a codimension 1 defect that has a 3D one-form SPT living on it, basically an SPT under this bulk Z2 one-form symmetry, and we can ask what happens when we then gauge this 4D system that has a 3D defect in it. And the result essentially is that when we gauge this system, we obtain a 4D topological order that has a 3+1d invertible defect embedded in it. So essentially this one-form SPT is dual to an invertible defect of the 4D two-form gauge theory. Okay, so to understand this defect, we sort of have to take a step back and look at pure 3+1d Z2 one-form SPTs. So it's known that in 3D, Z2 one-form SPTs have a Z4 classification. So we can label these one-form SPTs, we can call them M equals 0, 1, 2, or 3 SPT states. And the SPT that is relevant to this story is essentially the M equals 1 SPT. And basically, sort of the key fact which enables us to do this calculation in the first place is that when the M equals 1 SPT is gauged, when the one-form symmetry is gauged, we obtain a particular 3+1d twisted Z2 two-form gauge theory. And this gauge theory is actually precisely described by the Walker-Wong model based on the chiral semyon or 1s anion theory. And so what this means is that when we have this SPT state embedded in the bulk 4D system and then gauge the symmetry, essentially we obtain an invertible defect, which is in a certain sense described precisely by this chiral semyon Walker-Wong model. Okay, so to understand the nature of this defect, let me just quickly review the sort of important properties of this Walker-Wong state. So the Walker-Wong model is a spin model with with spin halves on the edges of a 3D lattice, and the ground state is essentially it's an equal weight superposition of closed loop states with phase factors that are assigned according to the topology of the loops in a particular state. So so there's a factor of I associated with twisted loops. There's an overall -1 for any given loop, but the sort of key property which we'll focus on is that there is a -1 phase that is associated to every pair of linked loops. And this is basically reflecting the -1 mutual braiding statistic of the semyon in the chiral semyon input anion theory. And so this -1 associated with linked loops is essentially crucial. Basically, what it implies is that the ground state should actually not be regarded as a condensate of loop objects. It should really be regarded as a condensate of disk-like objects, so basically each disk is a loop that bounds a certain membrane. And what this membrane does is basically measure the flux of strings penetrating the surface. And this is essentially a consequence of the fact that there's this -1 phase associated with linked loops. So okay, so
Yeah, Wilbur, just try to finish up.
Sorry.
Just try to finish up kind of.
Yeah. So okay, so essentially, with this knowledge in mind, we can ask what is the nature of this sort of invertible defect in 4+1d system that's associated with this Walker-Wong model. Well, essentially, the idea is that when an M membrane intersects this kind of invertible defect, this essentially corresponds to sort of adding a loop to the Walker-Wong wave function. But as we saw, it's actually not possible to add sort of a loop object. Essentially, we can only add a loop that is sort of attached to a membrane. And in the 4+1d system, this membrane, this blue membrane, is precisely an E membrane. So what this implies is that when an M membrane passes through this invertible defect, it must pick up an E membrane and therefore becomes a psi membrane. Okay, so this is an invertible defect, but if we want to construct this explicit local unitary U, which realizes this duality, we essentially have to convert this invertible defect into a local unitary. And the way we do this is basically by we sort of imagine a single gate, quantum gate, that creates a small bubble surrounded by this invertible defect. And then we essentially tile this bubble throughout the entire 4D bulk system. And in doing so, we obtain this so-called bubble circuit. So this is sweeping a lot of technical details under the rug, but this is essentially what we do. And we have explicitly carried out this procedure and have explicitly constructed this circuit U. And what we find is that indeed this bubble circuit U preserves the ground space. It maps closed membrane operators in this way, and on excited states correspondingly maps loop excitations in this way. And so for this reason, we say that this unitary is a hidden duality of the 4+1d loop-only toric code. So let me just end by sort of posing some questions. So the existence of this duality sort of raises some very obvious questions. So I would say maybe the first question is there some sense in which this duality can be interpreted as a bona fide automorphism of some TQFT? And secondly, what does this result imply about the notion of self-statistics of loop excitations in 40 topological orders. It certainly perhaps hints at the possibility that that there is no well-defined notion of self-statistics of loops in 4D, but it would require, I think, more careful thought to make any conclusive statements of this kind. So thank you.
Awesome. Great. Thank you, Wilbur. Let's go to questions. So Dom